I wanted to encourage students to avoid or to get beyond solving a problem by finding a similar problem and copying it. I know that a lot of students work this way. The first approach to a problem is to try to find an exact match. And another approach is to memorize a list of different chemistry problems that you've come across. This one multiplies, this one divides and then multiplies, and the list just gets too long. A better approach is to find a problem-solving strategy that can be applied more broadly. And unit conversions is a good strategy that can be applied to a lot of different chemistry problems. So let's take a look at that. So here in section 1.6, we're learning an approach to conversions, and a lot of stuff that we're going to be doing in Chem 101 can be looked at as a conversion. So the steps are to look at what you're trying to convert, come up with the relationships that you know. How are these things related that you can convert from one thing to the other? For every relationship you have, you can write two possible conversion factors. So you can write both of them and then choose which one you need. As you're doing the problem, keep the units next to all of the numbers. Don't just work with the numbers and then put the right unit on at the end. If you look at what the units are doing, you can catch mistakes. And then at the end, you can check on what your significant digits should be. Here, the first step is pretty obvious. It tells you what you're trying to convert. You have a length of 8.50 inches and you want to convert that to centimeters. You're also given your relationship. This one relationship can be written as two different conversion factors, depending on which you put on the top or on the bottom. The reason you're writing it like this is because you have two things that are equal, and if you have a numerator and a denominator that are equal, you have something that's equal to 1. And we can multiply this length, 8.50 inches, by something that's equal to 1 and not change the length that we have. The one we're going to choose in this case is the one on the right because it has inches on the bottom. So if we multiply this, the inches will cancel and we'll be left with centimeters. So that gives me 21.59 centimeters. The last step is to check significant digits. My original measurement only had 3 significant digits. The conversion factor is exact, so this has infinite significant digits. So our answer has to be rounded to 3 significant digits. And our final answer would be 21.6 centimeters. All right, so I've turned this relationship for this next problem into two possible conversion factors. We want to convert 56.3 pounds without changing the amount that we have. We just want to talk about it in kilograms. In this case, the left side one would be more useful because the pounds will cancel. This is why it's helpful to have the units next to the numbers in the problem. If you had picked the wrong one, you would notice that your answer is pounds squared over kilograms. That's not what we want. We want the pounds to cancel and we want just kilograms, not pounds squared over kilograms. So we're left with kilograms and a lot of different digits. We only started with something that we knew to 3 significant digits, and the relationship that we're using here is not an exact relationship. It's a 3 significant digit relationship. We have another place in the textbook where we're told that 1 kilogram is 2.2046 pounds. So if we had a weight, a mass in pounds that we wanted to convert that had more than 3 digits, we should use this relationship that has 5 digits. But the relationship we used had 3 significant digits. In any event, we need 3 significant digits in the answer. And this comes out to be 25.6 kilograms. So for this one, 878 kilometers is what we're trying to convert. This other number, even though it's the first one listed, is the relationship. And these are the two conversion factors that I can write with that one relationship. There was a little bit of confusion if I write this 1. Some people think that there is a number with 4 significant digits and a number with 1 significant digit. So if that confuses you, you can just leave off that number. We're saying that there's 1.609 kilometers per mile. So this is a 4 significant digit relationship. And the one that would be more useful is this one on the right, so that the kilometers cancel. So we use the relationship 1.609 kilometers per mile, but we have it flipped. That way the kilometers cancel, and we end up with miles. We also end up with a lot of digits. Since we're multiplying a measurement with 3 significant digits by a relationship with 4 significant digits, we need to keep 3 significant digits. So this distance would be about 546 miles. All right, so an additional step that's needed when you do a metric conversion is that we need to know what the metric relationship is. So there are these 12 prefixes that you need to have memorized. And when you see a problem, it won't be telling you that a teragram is 10 to the 12th grams. So when I first learned these prefixes, I just kind of used a rhythm to help me remember. I just said deci, centi, milli, micro, nano, pico, femto, and I would sort of chant that to myself and just remember that that was 10 to the -1, -2, -3, and then after that going by threes, -6, -9, -12, and -15. So I haven't ever really found another good mnemonic for remembering these. I just sort of kept repeating them to myself until I remembered them. Once you know what the prefixes are, you need to know how to use them. We have the prefix milli, and what we need to remember is that milli means 10 to the -3. Once we know that milli is 10 to the -3, we need to make sure that we fill in the correct relationship. So if milli equals 10 to the -3, then milligram equals 10 to the -3 grams. So 1 milligram is 10 to the -3 grams. If you write it on the wrong side and say that 10 to the -3 milligrams is 1 gram, that is not true. So using this relationship is going to give you the wrong answer. So in addition to knowing the prefix, you make sure that you know how to write the relationship with that prefix. So nano means 10 to the -9. 1 nanometer is 10 to the -9 meters. Deci means 10 to the -1. So a deciliter is 10 to the -1 liters. So 1 deciliter is 10 to the -1 liters. Micro is 10 to the -6. A microsecond is 10 to the -6 seconds. Okay, killi is 10 to the 3, so a kilogram is 10 to the 3 grams. Once we have a relationship, it can be written as 2 different conversion factors. In this problem, we're converting 83.8 grams, so we're going to need this conversion factor to cancel out the grams. So then there are a few ways you can deal with the power of 10. You can put it in a calculator as a power of 10. You can remember that 10 to the 3 is the same as 1,000, and you can divide 83.8 by 1,000 that way. But in any event, the grams are going to cancel, and you're going to end up with kilograms, 0.0838 kilograms. Or if you write it in scientific notation, it's 8.38 times 10 to the -2. Okay, our relationship here is that a microliter is 10 to the -6 liters. And that one relationship can be written as 2 different conversion factors. The conversion factor we need is this one because we want to cancel the liters and end up with microliters. So again, you can put this in your calculator, or if you want to, you can remember that 1 over 10 to the -6 is the same as 10 to the 6 over 1. When you flip something to the other side of a fraction, you're going to change the sign of that exponent. So there are 10 to the 6 microliters in 1 liter. And so the liters cancel and you are left with microliters. However, this is not finished because this is neither standard nor scientific notation. So let's bring down the 10 to the 6 and then let's write 0.087 the correct way in scientific notation. So that is 8.7 times 10 to the -2. And so if we wanted to write this answer in scientific notation, it's 8.7 times 10 to the 4 microliters. If we write it in standard notation, it's 87,000 microliters. So for this last problem, C, We don't have a direct relationship between nanometers and gigameters. Some people are really good at the metric system, so they might be able to figure one out. The way I usually think about it is in 2 steps. So I know that a nanometer is 10 to the minus 9 meter, and these are the 2 conversion factors that come from that relationship. And a gigameter is 10 to the 9th meters. So here are those 2 conversion factors. And we are starting with 63.11 nanometers. Actually, let's try starting with this in scientific notation, because that might make it easier. Let's see if that helps people out. So we have 6.311 times 10 to the 1 nanometers. So now for this one, I'm going to use this conversion factor. That will cancel nanometers and get me to meters. Now I want to cancel meters and get to gigameters. So our nanometers cancel and our meters cancel. We're left with gigameters. So hopefully you can do this in your calculator. Otherwise I collected all of the powers of 10 together. 10 to the 1 and 10 to the minus 9 multiplied together will give 10 to the minus 8. 10 to the minus 8, a negative 8 minus 9, because the 9 is in the denominator, will give a minus 17. So we have 6.311 times 10 to the minus 17 gigameters. Temperature conversions are a bit different. I wanted to address them separately. The thing about temperature conversions is there's not a direct relationship. You can't write a direct relationship for a temperature like you can for an inch and a centimeter. An inch is 2.54 centimeters. If you double the inches, you're going to double the amount of centimeters you have. We don't have as straightforward a relationship among temperature scales because in addition to the degrees being a different size for Celsius and degrees Fahrenheit, there's also an offset. For degrees Celsius and Kelvin, there's only an offset. The degrees Celsius are the same size as Kelvin. It's not actually degrees Kelvin. But here's a diagram in your book in section 1.6 that shows this. The 100 kelvins and 100 Celsius degrees are the same size, but 100 Celsius degrees are equal to 180 Fahrenheit degrees. That's why we multiply that Celsius by 1.8 to get the Fahrenheit. But then we also have to add 32 because it's offset. 0 degrees Celsius is the same as 32 degrees Fahrenheit. The way I remember these formulas are that the temperature in degrees Fahrenheit is going to seem larger than the temperature in degrees Celsius. If you look at Celsius, it's usually a smaller number for room temperature. And so in order to make the Celsius number bigger to convert it to Fahrenheit, I remember that you have to multiply because that's going to make it bigger, and you have to add. Then once I have come up with this formula, then I go ahead and subtract 32 from both sides, and then I divide both sides by 1.8. That gives me the Celsius alone, and it gives me degrees Fahrenheit minus 32 over 1.8. So in case that trick helps you remember which formula is which, you can use that. Another trick I know is that the Kelvin is never negative, so if I'm figuring out Kelvin, I don't want to subtract because I might go negative if I subtract. So for Kelvin, I'm going to add, and then for Celsius, I'm going to subtract. I should point out that I believe this is also exact. I have this error in the notes. So these conversion factors are not limiting you. You don't have to go down to 2 significant digits or go down to the ones place when you're using these formulas, and you don't have to go down to 2 past the decimal when you're using this conversion. All right, so let's try one over here. We're going to take a Fahrenheit temperature and convert it to Celsius and to Kelvin. The Fahrenheit temperature is known to the ones place or has 3 significant digits. So here's our 375. We subtract 32 and then we divide by 1.8. So we have uncertainty in the ones place. So our original number 375 has uncertainty in the ones place. The 32 has no uncertainty. It's exact, so it actually goes out into infinity. There's no uncertainty there, but the answer also has uncertainty in the ones place. Our next step is to divide. We're dividing something with 3 significant digits by something that is exact, which has infinite significant digits. And so our answer is going to have 3 significant digits. So that gives us 191 degrees Celsius. All right, for Kelvin, we're going to add our degrees Celsius to 273.15. Our degrees Celsius has uncertainty in the ones place, so when we add this, we are going to round it to the ones place. So our 464.15 is just going to become 464 Kelvin. All right, so let's go ahead and try another one. We have a temperature of 29 degrees Celsius. We're trying to convert it to Fahrenheit. We have something with 2 significant digits being multiplied by something that is exact. When we round the answer to 2 significant digits, we get 52, and then we add 32, and we get 84 degrees Fahrenheit. When we convert it to Kelvin, we add 273.15 to the 29, but the 29 has uncertainty in the ones place, so we should really report this to the ones place. 302 Kelvin. This next problem, we have the temperature in Kelvin, and we are trying to convert it to degrees Celsius and to degrees Fahrenheit. So we take our 77 Kelvin and subtract 273.15. That gives us negative 196.15, but we are just reporting to the ones place, so we can round this to negative 196 degrees Celsius. Then we'll go ahead and use that in this equation. To get Fahrenheit, we take our degrees Celsius temperature, which has 3 significant digits, multiply it by something that is exact. We end up with something that has 3 significant digits. So we have something with uncertainty in the ones place now because of the 3 significant digits, adding the 32, and then we end up with something with uncertainty in the ones place. So we have an answer of negative 196 degrees Celsius, negative 321 degrees Fahrenheit.